Welcome back to another video. Here, we will talk about point estimators. A point estimate is a single numerical value used to approximate an unknown population parameter, for example, theta. This value is calculated from a statistic, for example, theta hat, which is derived from sample data. The statistic used to calculate the point estimate is called a point estimator. For example, the sample mean x bar serves as the point estimator for the population mean mu. The sample variance, s squared, is the point estimator for the population variance, sigma squared. The sample proportion, p bar, serves as the point estimator for the population proportion, p. The difference in sample means, x1 bar minus x2 bar, serves as the point estimator for the difference in population means, mu1 minus mu2, and finally the difference in sample proportions, p1 bar minus p2 bar, serves as the point estimator for the difference in population proportions, p1 minus p2. While point estimates provide a concise and practical way to estimate population parameters, they are subject to sampling variability and do not account for the uncertainty inherent in the estimation process. When estimating a population parameter using a single number derived from a sample, the best estimate is the sample statistic, as it provides the most representative approximation of the population parameter. However, due to random variation, sample statistics almost never exactly match the true population parameter. Despite this limitation, they are regarded as the most reasonable best guess on average. This concept can be compared to a skilled shooter aiming at a target. While individual shots may not always hit the bullseye, the shooter consistently aims close to it on average. Similarly, point estimates are concise and practical tools for approximating population parameters, but they are subject to sampling variability and do not account for the uncertainty inherent in the estimation. Examining the proposed point estimators from the previous slide, we observe that their expectations align with the parameter of interest. This alignment reflects the statistical interpretation of a best guess on average, emphasizing that unbiased point estimators center around the true population parameter. Case in point, we can see that the expectation of x bar is mu. Here we can see that the expectation of s squared, which is the point estimator for population variance, is sigma squared. Although s squared almost never exactly match the true population variance, but it provides the best guess on average. A point estimator is considered unbiased if the average of its estimates over repeated random samples equals the true population parameter. In other words, the expected value of the estimator matches the true parameter. This means that, on average, the estimator does not systematically overestimate or underestimate the parameter. It provides accurate estimates in the long run. If the estimator is not unbiased, the difference between its expected value and the true parameter is called the bias of the estimator. For example, if the expected value of the estimator is greater than the true parameter, it consistently overestimates the parameter. While unbiased estimators are desirable because they are accurate on average, a biased estimator can still be useful if the bias is small and the estimator has other advantages, such as lower variability. Among all unbiased estimators of a population parameter, the one with the smallest variance is called the minimum variance unbiased estimator, or MVUE. This means that, while all unbiased estimators provide accurate estimates on average, the MVUE is the most reliable because it has the least amount of variability across different samples. In other words, it is the most precise, unbiased estimator. For example, if we have a random sample of size n drawn from a normal distribution with a specific mean and variance, the sample mean is the MVUE for the population mean. This makes the sample mean not only an unbiased estimator of the population mean, but also the most consistent and precise among all unbiased estimators of that parameter. What is we have two options. One point estimator with low bias but high variance, and another one with high bias and low variance? Which one is better? MSE can help us to answer this question. The MSE, mean squared error, of an estimator is a measure of how accurate the estimator is in estimating the true population parameter. It is calculated by averaging the squared differences between the estimator's values and the true parameter value. The MSE takes into account two components: the bias of the estimator, how far the average estimate is from the true value, and the variance of the estimator, how much the estimates vary from sample to sample. In essence, the MSE combines both the accuracy, low bias, and precision, low variance of the estimator into a single measure. A smaller MSE indicates a better estimator because it means the estimates are both close to the true parameter on average and have little variation across samples. For an unbiased estimator, the MSE is equal to its variance, as there is no bias to contribute to the error. Previously, we discussed that if our sample size is big enough, we can claim X bar approximately follows a normal distribution. But we didn't discuss why Z defined as X bar minus mu divided by sigma over square root of n follows a standard normal distribution. Here, we can see that we can easily find the expectation and variance of X bar. Expectation of X bar is mu, the mean of the original distribution, while the variance of X bar is the variance of the original distribution divided by square root of n. If X bar is following a normal distribution with parameters mu and sigma squared over n, we can standardize X bar by subtracting the mean and diving this subtraction by the standard deviation. As a result, if X bar is approximately following a normal distribution, then Z should approximately follow standard normal distribution. Thank you for listening to this short lecture on point estimators.